Now we are going to start with the working part of the DC motor. But before that, the students are advised to watch the previous video regarding the concepts which you need to know before understanding the working of the DC motor. So those concepts, they are really very important to understand this working of the DC motor completely. So we are straight away starting with the working part of the DC motor. So in DC motor, we are again having this U-shaped electromagnet. This is North Pole, this is South Pole. There is an armature which is present in this, like this. So this is the armature. This is further connected to split rings. They are having the brushes which are pushed against these split rings. These brushes help us to make the connection with the external circuit. So battery, rheostat and key. Alright, there is an axle which is present here, and we'll label some soft iron core around which it is wounded. Alright, let us label this armature as ABCD. These are the distances as R1. This is the distance as R2. These are split rings as S1 and S2, and brushes as B1 and B2. Now magnetic field is always from north to south outside the magnet. So this is north to south outside the magnet. When we switch on the current, this is going to flow in this circuit like this. Alright. Now we have to see which rule we'll have to apply. If we know that there is the presence of magnetic field and there is the flow of current, we know two things: the direction of magnetic field and direction of current. Two things are known, and the third thing, that is the force, we need to find out, which tends to or which makes this armature to rotate. We'll have to find out the force only, and we know the magnetic field and the direction of current. Then we'll only up to a rule which is known as Fleming's left hand rule. So we'll simply apply the Fleming's left hand rule. In the previous video, we have discussed that the Fleming's left hand rule will only be applicable on this arm AB and this arm CD, and it will not be applicable on this arm AC. So we are straight away starting with the working part, and we are starting with the starting position of this motor. In the starting position of this motor, armature is like this. The position of armature is like this. So this angle is 0 degree. That is, the angle between this plane of armature and magnetic field line is 0. This has also been discussed in the previous video. So this is the starting position at 0 degrees. Alright. At 0 degree, we are considering what is happening on this arm AB. On this arm AB, current is flowing from bottom to top. Current is flowing bottom to top. So bottom to top is the current. So I am applying current as this. Current is flowing bottom to top on arm AB. Magnetic field line is left to right. Magnetic field line is left to right as B. Alright, let me write it also. This is magnetic field. This is the current. So current is bottom to top. Magnetic field line is left to right. Alright. The Fleming's left hand rule says point your forefinger in the direction of magnetic field and central finger in the direction of current. The direction in which the thumb will point will give you the direction of the Lorentz force. So magnetic field line is left to right. This is my left hand. Magnetic field line is left to right. So forefinger is in the direction of the magnetic field, which is left to right. The central finger will point in the direction of current. Central finger is now pointing in the direction of current. Current is bottom to top. So magnetic field here, current is bottom to top. Current is bottom to top. The direction in which the thumb will point, will give the direction of Lorentz force. So thumb is moving away from your side, or I can say it is moving inside the board. What does that mean? That on arm AB, there is force which is pulling this arm AB inside the board. So the force, the Lorentz force, is pulling the arm inside the board according to this rule. So Lorentz force, let me give it a name as F1. This is in the direction inwards. The AB is pulling inwards. Alright, so let me write it down here also. It is moving in, and the name of the force is F1. When magnetic field is left to right, current is bottom to top, this thumb is going to move inside, which means the AB arm is pulling inside the board. Alright. And the magnitude of this force we have already discussed. It is B into I into L, where B is magnetic field, I is current, and L is the length of conductor, this AB. Alright. Now we'll skip AC. You know why? Because in the previous video we have completely discussed that part in detail. So next is on arm CD. Let us talk about on arm CD. On arm CD, current is moving from top to bottom. Current is moving from top to bottom. So this is the current. Magnetic field is still left to right. Magnetic field B is still left to right. Now we need to find out this force. What is this force? Let me give this force name as F2. Now let us see. Forefinger in the direction of magnetic field. Forefinger in the direction of magnetic field. So magnetic field is left to right. Magnetic field is left to right. Current is top to bottom. Current is top to bottom, which is like this. Magnetic field is left to right. Current is top to bottom. So central finger in the direction of current. The direction in which thumb will point will give you the direction of the application of Lorentz force. So forefinger magnetic field, left to right, central finger top to bottom, and this force is moving out. Means it is moving out from the board, or it is pointing towards your side. Which means the arm CD tends to move out from the board, because Lorentz force, the Lorentz force is acting on this arm CD in the direction away from the board. So it means CD arm is pulled outside the board. It is moving on your side. So CD arm is moving out. CD arm is moving out. Let me name it as F2. Let us name it as F2. So this F2 is outwards. This F2 is outwards. Now, what is the magnitude? Magnitude of this is again same as B into I into L. We haven't changed the magnetism. That is, whatever B is used here, the same B we are taking in this case. Current has not changed. So I is same. Length, AB and CD, they are equal. So we haven't changed the length. So it means these two forces, they are equal. So let me write it down as here. F1 and F2, they are equal. They are equal, but their direction is opposite. If one is taking the coil in, the other is taking that coil out. So they are equal in magnitude, but opposite in direction. Opposite in direction. Equal in magnitude, but opposite in direction. Now this thing has made us to recall one more thing that we have discussed in some chapters. If this is you would say a rod, on this, one force is applicable on this side, other force is applied on this side. They are equal in magnitude, but the direction is opposite. One is moving top to bottom, other is moving bottom to top. And there is sufficient distance between these two. There is some distance between these two. What will happen? This will create a turning moment, or which is simply known as torque. It will result in the formation of the turning moment torque. Why? When two forces, they are equal in magnitude and opposite in direction, and there is some distance between these two forces, it forms a couple. these forces here which are equal and opposite, it is known as the couple, and this couple tends to rotate this rod in any direction depending on the application of force, whether in clockwise or anti-clockwise. So what I want to convey here is, if there are two forces equal and opposite, equal in magnitude, opposite in direction, and there is some distance of separation between these two forces, it will tend to rotate that conductor. Here the conductor is the armature. The two forces are F1 and F2 Lorentz forces. We have seen they are equal in magnitude but opposite in direction, and there is distance of separation also between these two. So this also fulfills the direction of the couple formation. If the couple is formed, these two forces, they are known as couple, and when the couple is formed, the torque will be generated, which means the turning moment is created, and this armature will start to rotate because of this generation of the torque, and this torque is generated by this couple which is created from this Lorentz forces. Alright. When this is, let us say this is the side AB, this is the side CD. If AB is moving in and CD is moving out, it tends to rotate it. It tends to rotate it in this direction. If this is the angle 0 degree, we'll say this is the angle 90 degrees. When the plane of coil, this is the plane of coil, it is in the direction perpendicular to the magnetic field line. Here magnetic field line was here and plane was in this direction, parallel 0 degree. When it has made its first rotation, now it has come to the position of 90 degrees. Alright, why it has rotated? Because this force is pulling this side inside and pulling this side outside. So it tends to rotate in this direction. It is rotating in this direction. So till now we have only considered about the case of 0 degrees. We have just considered the case of 0 degree when this is here and it has made its first rotation of 90 degrees. So the next thing that we will be going to start is when the position of the armature is at 90 degrees. So let me clear some portion of the board and then we'll start with its rotation at 90 degree. What will happen? Alright, now we are going to start with its rotation at 90 degrees. At 90 degree, what is going to happen? If this armature has taken its first turn of 90 degree, it has taken its first turn to 90 degree. See, very important thing is going to happen. We know these brushes B1 and B2, they will remain at that position only. These B1 and B2 brushes, they are stationary. B1 and B2 brushes are stationary. They are stationary. They cannot move. But these slip rings, they can move. And when it has made its first rotation, this AB has moved in and this CD has moved out. What is going to happen? This split rings, they are also going to turn. So if these split rings, they are on this position, after 90 degree rotation, they have turned like this. After 90 degree rotation, they have turned like this. When they are turning like this R1 and this R2 is going to be in these sides. They are going to be on these two sides. R2 will move out, R1 will move in, or you would say this split ring S2. This is going to be placed like this. When it is moving out, this is the S2 which is there and this is the S1. So S1 has moved in and S2 has moved out. But this external circuit is still at its position. It has not moved along because these brushes, they are the stationary part. This S2 has moved out and S1 has moved in, S2 and S1. When this is going to happen, this will disconnect this armature from the external circuit because they are at this position intact. These split rings along with this armature has made a turn. It has turned to 90 degree. When it has turned to 90 degree, this circuit till here is present here only, but this internal circuit has moved. When this is moved, it breaks the connection with the external circuit. So connection of armature breaks with external circuit. When it breaks with the external circuit, no current is now flowing, which means the motor will stop? No, the motor will still rotate because this motor is having its own inertia. This motor is having its inertia. Now, if this is having that couple which deflects it or which makes it rotate, when it is happening like this and it makes its 90-degree turn, at this moment only it is disconnected from this circuit. But because it is still in the motion, it will remain in the state of motion for some time, and that is known as the inertia of the body. It will not stop at this. Even if the circuit breaks, it will not stop its rotation because there is the inertia of this moving armature. So it will take one more turn. Because of its inertia, it will take one more turn. And by taking its one more turn, it has reached to the position of 180 degrees. So it has reached its position of 180 degrees. Again, when this is like this, it has undergone its first turn. When it has taken its first turn, this split ring S2 moves out, split ring S1 is inside. This external circuit is at its own position, which it is initially at. So this circuit is at its own place. Only this thing it moves. When this thing moves, it breaks its connection with the external circuit. If that is going to happen, the connection breaks, no more current is flowing, deflecting couple or that Lorentz force is not acting, but still it will remain in the state of motion because of the inertia. Because of inertia, it will take one more rotation and it will reach to the position of 180 degrees. So this is the working part 1 of this, you would say, DC motor. In the next part, we'll make this till 360 degrees and then we'll complete or conclude the direction of motion of this motor.